So last time we just talked about the statements. We um, introduced a definition of statements, and then the compound statements with some uh, symbols. Um, I think it's called a logic connective or something, right? You can make a compound statement by using those symbols, and you can make it as complicated as you want. Okay. Uh, you can have one or more logic connectives with one or more statements to make compound statement. Again, if you still remember, a statement means that you can precisely tell whether the statement is true or false. It has a definite value for truth value. And so that excludes a lot of sentences from the statements. Today we're going to continue with the topic of statements, and we're going to start logic equivalences. In some cases, we wish to show that two compound statements are essentially the same. So then we call these two statements equivalent. So the definition of logical equivalence is 3.23 definition. Two compound statements are logically equivalent if they have the same truth value regardless of the truth values of the components. Well, generally we're talking about compound statements, but maybe you just have one statement equivalent to a single statement without compound. That can happen also. So in other words, they don't have to be both compound statements when we talk about logical equivalencies. So if R and S are compound statements that are logically equivalent, we write R equal to S. We usually don't write the equal signs like in numbers in logic. But instead, we use three horizontal lines to mean they're equivalent. Mathematically, you can think it as of equal. Okay, and so for example, if you consider, the and so suppose we have two statements P and Q, and if you make the intersection or I think it's called what? What's the name of this? Conjunction. Okay, conjunction. Okay, that's called a conjunction. But it's like an and. So, and then you take the negation of the whole thing, then that will equivalent to the disjoint or negation of P or disjoint with negation of Q. Okay. And we claim these two statements R and S are equivalent, those two compound statements. And what it means is whatever the truth values of the components P and Q, you always get a truth value for the compounded statements. I mean, the same, okay. The same truth table, basically, with those two compound statements. Whatever the truth values of the components of statements P and Q, you're going to get always the same truth values for RNAs correspondingly. So you can see for P, the statement can be true or false, and the same for Q. So then we can make combination of P and Q. Then there are four possibilities as we did before. P true, Q true, P true, Q false, P false, Q true, P false, Q false, and then you just find out the truth values of those two compound statements we have here on S. So let's just do P and Q first. Conjunction P and Q. So it means when P and Q both are true, then P and Q is true. Otherwise, it's false, right? So if you negate this P and Q, then you just flip true and false in P and Q. So we got the first row false and the other row is true. So that's the truth table for the statement R. And then we just calculate or find out the truth table for the compound statement S. So we would take a negation of P. So just flip the truth table of P. So we got 2 false in the first two rows and the 2 true on the other two rows. Similarly, we can take a negation of Q. So we get first row and the third row false, and second row and the fourth row true. Okay, if we just flip the truth table for Q, and then you're going to take the disjoint or union, whatever you call it, or So whenever both components are false, then the union or the disjoint is false. Otherwise, it's true. So we got the first row false and the other three rows true. So you can see this is exactly the same as the truth table of negation of P and Q. And we have already listed all the possibilities for the combinations of P and Q in the truth values. So that means these two compound statements, we call them RNAs equivalent. Okay. That means, you can replace one with the other. All right. So they're equivalent. So that's a simple example. So here in theorem 3.26, we just listed some logical equivalencies in here, 10 of them. So we have PQR 3 statements. The first logical equivalence is if you negative P and negative P again, you get P back. And that's called double negation. That's just like when you take the negative of a number, then you make the negative of that again, it becomes original number. Okay, but then to show it, you can draw the make the truth table for P. For P, we only have one component in this compound statement. So then when you make the truth table, it only has two rows, one row for true and the other row for the false, and then you can easily find out the equivalence of those two statements easily. When you negate the truth value of P, it becomes the other value, and then you negate it again. So it brings you back the original, change back to the original truth value of P. So that's the first equivalence. And then we have 2 and 3 called De Morgan's law, as you already know, when you take a negation of P and Q and negation of P or Q, then you're going to negate each component and then take the union or disjoint, or take the intersection or conjunction of the two negations, all right, respectively. And then the fourth one is called the contrapositive law in logic. So we have a conditional statement P implies Q. Then this is logically equivalent to the statement of negation of Q implies negation of P. All right. Okay, that can be easily again proved by drawing the truth table for P and Q. All right. And the fifth and the sixth are called distributivity, like the numbers, when you multiply and add. Okay. So if you take the disjunction of two statements and then you do the conjunction of it with another statement, and then you can actually distribute the third statement into the conjunction of the first two statements. So that's equivalent to the disjunction of P and Q and P and R. Okay, just distribute P and the conjunction into Q and R respectively. And similarly, if you do the disjoint of a conjunction of two statements with another statement, you can also distribute the third component or statement into the Q and R of the conjunction. Okay, distribute the disjunction, the statement and the disjunction into each component of the conjunction. So that's another version of distributivity. Okay, and you can always think of those correspondence in numbers. All right, and the seventh and eighth are called the associativity. It essentially says if you're trying to make the conjunction of three or more statements, components, then you can do either two first. Okay. You can group the first two statements and take the conjunction and then do the conjunction of it with the other statement, or you can do the conjunction of the second, third statements, and then take the conjunction of it with the other statement. And same for the disjunction. Okay. Some of those rules are pretty obvious. Some of them you already learned before, like De Morgan's law, and maybe you can partially, but some of them may not be so obvious, and it's easy to get confused and make mistakes. So if you're not sure about whether you are using the right rule or not, then just check this table, okay? And the last two logical equivalences are just the commutativity, If you try to make the conjunction or disjunction of two statements, the order is not important, of course. When we do the truth table, it really doesn't matter which one goes first for these two connectives, right? Or operations. Any questions about this table or theorem? If not, then let's just look at one example. I'll just prove one of them. For example, number 7, the associativity. P and parentheses Q and R parentheses back equals parentheses P and Q parentheses back and R. Okay, let's just prove that. So again, we just make a truth table, but this time we have three component statements, P, Q, and R. So you want to show that if we take the conjunction of P and Q first, and then take the conjunction of it with R, it should be the same as we take the conjunction of Q and R, and then take the conjunction of it with P. So just list the choose values for each component P, Q, R, and then this time we're going to have 8 rows that will covers all the possibilities of the choose values of the 3 components or statements. So, in the first 4 rows, the choose value for statement P is true, and the other 4 rows is false for P. And then in the second column, the choose values Q are taken true for the first 2 rows and 5 and 6 rows, and then false for 3rd and 4th rows, and 7 and 8 rows. Finally, the choose value for statement R is just taken true and false alternatively from first row and to the end row, okay, to the last row. So then we just do a P and a Q, or P conjunction Q. So you just look at the first 2 columns and see the choose values for P and Q. So for the first 2 rows, both P and Q are true, so we get the 2, we'll say, first 2 rows. And then for the other rows, you can see, each of the rows contains at least one false from either P or Q. So that makes all of them false. All right. And then you want to take the conjunction of P and Q with R, and so and the first row will be true because both of them will be true, but then you see all the other rows are false. Actually, if you look at the second row, R is false, so that automatically makes the whole thing false, and the other rows below it in P and Q are false. So that makes everything false again. So we got all the false except the first row. And then we want to do Q and R first. So just do this things again in a Q and R. The first row and the fifth row are true. Q and R are both true on those two rows, but the other rows are false. Either Q is false or R is F or false in those rows. So then we get 3 false. From row 2 to row 4, and 3 rows of false from row 6 to 8. And then you take the conjunction of P and the Q and R. So you get a P, the first row is true, and the Q and R is true. So that makes it true for the whole thing. And then if you look at all the other rows, then you can find either P is false or Q and R is false. Okay. Actually from row 2 to row 4, P is true, but Q and R is false. So that makes the whole thing false. And then from 5th row to the 8th row, P is false. So that makes everything automatically false. So again, we get the first row true and the other rows false, which is exactly the same as P and Q first and R. Okay, so this proves the equivalence of those two compound statements. All right. So that's how you prove logic equivalence. You have to make the truth table, basically. Okay, the last thing we're in this section is called tautologies and the contradictions. We're going to talk about contradictions first. So sometimes the truth value of a compound statement does not depend on the truth value of the compounds from which it is composed. And we say, different names for those special cases of compound statements. So definition 3.29 says a compound statement that is false for every possible combination of truth values for its components is called a contradiction. So whatever the truth value of the components of the statement of the compound statement, the truth value of the compound statement is always false. So that can never be true. So obviously that's contradiction. So the compound statement is always false. So that's why it's called contradiction. So for example, if P is a statement and the compound statement P conjunction with the negation of P is an obvious false. Regardless of whether P is true or false. I mean, this is easy to prove. You only have 2 rows again, P, because you only have one component in this statement, compound statement. So Whenever P is true, then negation of P is false. Or vice versa. So if you take the conjunction of them, obviously you're going to get false always. So one thing cannot be true and false at the same time, right? That's logically not possible. That's what it means by logic, in some sense. Okay. And the other thing is called tautologies. A compound statement that is true for every possible combination of truth values of its component is called a tautology. Okay, so this is the right opposite of the contradiction. Whatever the compound statement, the components of the compound statement, the compound statement is always true. Okay. So it really does not depend on truth values components. For example, let P a statement, then the compound statement P implies P is a tautology. Okay, that's pretty easy to see, right? Again, you can make a truth table with two rows. When P is true, then true implies true. That is itself the compound statement itself is true. Okay. Because the only case this conditional compound statement is false when P is true and the other statement is false. But this will never happen because whether P is true or false, you always get the same truth value for the two statements. Actually, only one statement P. So you can never get different truth values for the two statements. So it has to be true every time. Okay, the last example is something like this. Okay. So we claim this compound statement with two components, P and Q, is a tautology. So, if you have a conditional statement, P implies Q, and then you do the conjunction with P, that makes a compound statement itself. And if you make another statement from it by implying to Q, so then you make a new statement from the whole thing, and it turns out that the last component statement is a tautology. It has to be true every time. And we can prove it easily from the truth table again. So we have two components, so we can use the first two columns as the truth values P and Q. So once again, we just take it true for the first two rows for P and the third and fourth rows for false for statement P. And we just take true and false alternatively in the 4 rows with truth value of Q, and then just do the steps of this compound statement one by one and see what happens at the end. So P implies Q, that's a compound statement. It is false only when P is true and Q is false. So the only case of this compound statement is false is the second row. Otherwise, it will be true for other rows. Okay, so that's that. Then we take the conjunction of that with P. So we need to look at the truth values of P this time also. So In the first row, both of them are true, so the conjunction is true. And in the other rows, you can see either P is false or P implies Q is false. So all the other rules are false, right? Okay. So then from that compound statement, we just make the final compound statement by adding implying Q in here. So then, then we have to look at the third column and the second column. Okay, looking backward, because the first compound statement is this P and P implying Q. Okay, so it is true in the first row, and Q is also true in the first row. So that makes this conditional statement true. All right, true to true. That's true. And then in the other three rows, the P and P implied Q is false. So that automatically makes the final thing, the whole thing true, because the only case when this thing is false is when the first part is true, but the second part is false, and that never happens. So at the end, all the rows are true. Okay, and that has included all the possibilities for the choose values P and Q. So so it really doesn't matter whether P and Q is true or false. At the end, we always get this compound statement true. All right. I think it is a famous statement, logic law or something. So if, for example, if P is true and P implies Q, okay. So what it means is if P is true, then Q has to be true to be the whole thing true, for the whole thing to be true, right? Q cannot be false because that will make false. So then what happens is, if P is true, then Q has to be true for the whole thing to be true. And we know P is true in here in the first place. So then automatically that means Q has to be true. So that's what it means in here. Any questions for this section? So we just finished this section, and we're going to start a new section next time, next Monday. And let me just stop